You are moving right now, even if it feels like stillness. Not just through the air around you or along the surface of the Earth, but through the galaxy itself, at a speed of roughly 230 kilometers every second. There is no sensation of it. No wind, no vibration, nothing to suggest that your entire existence is courting motion. And yet, every second, you are carried thousands of kilometers through space, along a path that began long before you were born and will continue long after you are gone. This motion is not random. It is not drifting. It is an orbit. Somewhere far beyond the stars you can see, about 26,000 light-years away, there is a point that everything in the Milky Way responds to. Every star, every cloud of gas, every system of planets, all of it follows paths shaped by something hidden at the center. The night sky looks calm and scattered, but in reality it is part of a vast, rotating structure, slowly turning around a single, invisible anchor. For most of human history, we had no idea that anchor existed. When people first looked up and saw the Milky Way stretching across the sky, it appeared as nothing more than a faint band of light. Soft, diffuse, almost like a cloud. It was beautiful, but it did not suggest structure. It did not suggest motion. It certainly did not suggest that everything we know is bound to a single point far beyond our reach. Even as astronomy advanced and we began to understand that the Milky Way is a galaxy, a vast spiral system containing hundreds of billions of stars, the idea of a true center remained vague. There had to be one mathematically, a place around which everything rotated, but it was assumed to be unremarkable. Just a denser region of stars, brighter and more crowded than the rest. The problem was that we could not see it. Between us and the galactic center lies an immense barrier of gas and dust, thick enough to block visible light almost completely. When telescopes pointed toward the center of the Milky Way, they did not reveal a glowing core or a dense cluster of stars. They revealed darkness, not emptiness, but obscuration. Something was there, but it was hidden behind layers of material that light could not pass through. For centuries, the true nature of the galactic center remained concealed, not because it was distant, but because it was veiled. That changed in the 20th century, when astronomers began to observe the universe in wavelengths beyond visible light. Radio waves, unlike optical light, can pass through dust. They carry information from regions that would otherwise remain invisible. When radio telescopes were turned toward the center of the galaxy, they revealed something unexpected. A compact, intense source of radio emission. It was not spread out like a cloud. It was not diffuse like a collection of stars. It was concentrated, small, and unusually bright. Whatever it was confined to a region far smaller than anything that should produce that level of energy. It did not behave like a star cluster. It did not resemble gas. It did not match any known structure. This object was given a name based on its position in the sky, Sagittarius A. At first, the name carried no implication of what it truly was. It was simply a label for something that did not yet have an explanation. But even in those early observations, there were hints that this was not just another astronomical object. The brightness, the compactness, the stability of its position, all of it pointed towards something massive, something central, something exerting influence without being directly visible. The question was not just what it was, but how something so powerful could remain hidden. You cannot see a black hole directly. There is no surface to reflect light, no structure to illuminate. If something like that existed at the center of the galaxy, it would not announce itself in the way stars do. It would reveal itself through motion, through gravity, through the behavior of everything around it. So instead of trying to observe Sagittarius A directly, astronomers began watching the stars nearby. This became one of the most patient and precise experiments ever carried out. Using infrared telescopes capable of seeing through the dust that blocks visible light, researchers focused on a small region at the center of the galaxy and began tracking individual stars over time. Not hundreds or thousands, but a handful, each one carefully observed, year after year. What they found was not gentle motion. The stars near Sagittarius A were moving with extraordinary speed, tracing tight, curved paths around something invisible. Their trajectories were not random. They followed clear orbits, elongated and precise, like planets around a star, but far more extreme. The closer they passed to the center, the faster they moved, accelerating to velocities that could not be explained by any normal concentration of matter. One star, in particular, became central to the investigation. It was labeled S2, an otherwise unremarkable star except for its orbit. Over the course of 16 years, S2 completes a full path around Sagittarius A. That alone is unusual, but the details of its motion are what made it decisive. At its closest approach, it comes within a distance comparable to the scale of our own solar system, yet it moves at thousands of kilometers per second, a significant fraction of the speed of light. Only an immense, compact mass could produce such an effect. By tracking S2 and other nearby stars with increasing precision, astronomers were able to calculate exactly how much mass must be present at the center to hold these orbits together. The result was clear and consistent. Around 4 million times the mass of the Sun, confined within a region smaller than the orbit of Mercury. No cluster of stars could remain stable under those conditions. They would collide, disperse, or collapse. No cloud of gas could hold that much mass without emitting light or dissipating. Every alternative explanation failed under scrutiny. What remained was not a guess, but a conclusion. At the center of the Milky Way sits a supermassive black hole. What is striking is not just its existence, but how long it remained hidden. For billions of years, it has been there, shaping the motion of the galaxy, anchoring the orbits of stars, influencing the structure of everything around it, and yet it left no direct trace that could be seen with the naked eye. Even with telescopes, it revealed itself only indirectly, through the careful observation of motion and the application of physics. And even then, understanding what it is does not immediately explain how it came to be. A black hole with 4 million times the mass of the Sun does not form in the same way as smaller black holes, which are the remnants of collapsed stars. Sagittarius A belongs to a different category entirely, one that likely formed in the early universe, when conditions were very different from what we see today. There are several competing ideas about how such objects originate, but they all point toward a time when matter was denser, interactions were more frequent, and the seeds of galaxies were still taking shape. One possibility is that it began as a direct collapse, where a massive cloud of gas, instead of forming stars, collapsed inward under its own gravity, bypassing the normal stages and forming a black hole from the outset. Another is that smaller black holes, formed from the deaths of the first generation of stars, merged repeatedly over time, growing larger with each collision. There is also the idea that early galaxies, rich in gas and constantly merging with one another, fed material into a central region, allowing a black hole to grow rapidly in mass. What all of these scenarios have in common is time. Sagittarius A is not just massive, it is ancient. It has likely existed for billions of years, forming alongside the Milky Way itself, growing as the galaxy evolved, and remaining at its center as everything else moved around it. Long before the Sun formed, before Earth existed, before life began, This object was already there, exerting its influence in silence. And unlike many supermassive black holes in other galaxies, Sagittarius A is relatively quiet. In some galaxies, central black holes are active, pulling in vast amounts of matter and releasing enormous energy in the process. These are quasars, among the brightest objects in the universe, visible across billions of light-years. Sagittarius A is not like that. It is comparatively dim, emitting only small amounts of radiation, suggesting that it is not currently consuming much material. But quiet does not mean inactive. Even in its subdued state, Sagittarius A occasionally produces bursts of energy, brief flares likely caused by small amounts of gas or debris falling inward. These events are modest compared to the violent activity seen in distant quasars, but they are enough to remind us that the black hole is not dormant. It is still interacting with its surroundings, still shaping the environment at the center of the galaxy. And everything near it continues to respond. Stars trace their orbits, accelerating and slowing as they move along paths defined by its gravity. Gas clouds drift inward or are deflected, depending on their trajectories. Space itself, in the immediate vicinity, is no longer behaving in the simple, predictable way it does here. The closer you get, the more extreme the effects become, not just in motion, but in time, in energy, in the very structure of reality. All of this is happening continuously, whether we observe it or not. Because the truth is, we are not seeing Sagittarius A as it is now. We are seeing it as it was 26,000 years ago. The light that carries information from the galactic center takes that long to reach us, traveling across the vast distance between our position in the galaxy and the core. By the time it arrives, everything it represents has already happened, long before human civilization began to take shape. Which means that right now, in this moment, Sagittarius A is doing something. Stars are moving. Gas is shifting. Energy is being released or absorbed. But whatever is happening there now will not be visible from Earth for another 26,000 years. There is no way to bypass that delay. No way to see the present state of the galactic center. We are always observing the past, reconstructing events that are already long gone. And yet, despite that separation, we are still part of the same system. Every second, as you sit here, you continue along your orbit, carried by the combined motion of the Earth, the Sun, and the galaxy itself, all of it ultimately tied to that invisible center. The path is slow on a human timescale, taking hundreds of millions of years to complete a single orbit, but it is constant. It does not pause. It does not deviate. It simply continues. For decades, everything we knew about Sagittarius A came indirectly, through motion, through inference, through the careful tracking of stars and the application of physics. We could calculate its mass. We could map its influence. We could describe its effects with increasing precision. But we had never actually seen it, not even in the abstract way that black holes can be observed. That changed when a network of telescopes, spread across the surface of the Earth, began working together as a single instrument. The Event Horizon Telescope is not one telescope, but many. Radio observatories located in different parts of the world, from the high deserts of Chile to the volcanic slopes of Hawaii, from the mountains of Spain to the frozen plateau of Antarctica. Individually, each of these telescopes can observe the sky in radio wavelengths, but when synchronized with extraordinary precision, they form something much larger, effectively creating a telescope the size of the planet itself. This technique relies on interferometry, combining signals from distant locations to achieve a resolution that no single instrument could reach. The larger the effective diameter of the telescope, the finer the detail it can resolve. By linking observatories across continents, astronomers were able to reach a level of precision capable of detecting structures on the scale of a black hole's event horizon, even at distances of tens of thousands of light-years. The first success of this system came in 2019, when an image of the black hole at the center of the galaxy M87 was released. It appeared as a ring of light surrounding a dark center, a silhouette formed by gravity bending light into a circular shape. It was not a direct photograph in the traditional sense, but a reconstruction built from vast amounts of data, processed and refined until a coherent image emerged. Sagittarius A presented a more difficult target. Although it is much closer than M87, it is also far less stable in appearance. The gas surrounding it moves rapidly, changing brightness and structure on timescales of minutes rather than days. This variability makes it difficult to combine observations into a single, consistent image. It is like trying to capture a long-exposure photograph of something that refuses to remain still. To overcome this, astronomers collected enormous quantities of data over multiple observing sessions, then used computational techniques to account for the constant changes, effectively averaging the variations into a stable representation. The result, released in 2022, was the first image of Sagittarius A. What appeared was not a solid object, but a structure defined by light and gravity. A bright, uneven ring, formed by hot gas orbiting at extreme speeds, its light distorted and wrapped around by the curvature of spacetime. And at the center, a region of darkness, not because it emits no light, but because light from within that region cannot escape. This is the shadow of the black hole, the visible consequence of an invisible boundary. That boundary is known as the event horizon. It is often described as a surface, but it is not a physical barrier. There is no edge you could touch, no transition you could feel as a change in texture or resistance. Instead, it is a threshold defined by escape velocity. At that distance from the center, the gravitational pull becomes so strong that even light, traveling at the maximum possible speed, can no longer move outward. Outside the event horizon, light can still escape, though its path may be bent and distorted. Inside it, all paths lead inward. Not because something is pulling objects down in a conventional sense, but because the structure of space-time itself is curved in such a way that outward is no longer a valid direction. The size of this boundary depends entirely on mass. For Sagittarius A, with its 4 million solar masses, the event horizon spans roughly 24 million kilometers in diameter. This is large on a human scale, but small compared to the distances between planets. If it were placed at the center of our solar system, it would fit well within the orbit of Mercury. There would be no vast consuming sphere extending outward, no engulfing darkness reaching across the planetary system. But within that relatively compact region, the effects are absolute. Surrounding the event horizon is a region where light itself can orbit the black hole. This is known as the photon sphere. At this distance, gravity bends the path of light into closed loops, allowing photons to circle the black hole before eventually escaping or falling inward. The bright ring seen in the Event Horizon Telescope image is closely related to this region, formed by light that has been redirected multiple times before reaching us. It is not a simple ring, but a complex accumulation of paths, each photon tracing a curved trajectory through warped spacetime. Beyond this lies the accretion flow, the material that gives the black hole its visible structure. Gas, dust, and fragments of matter drift toward Sagittarius A, drawn by its gravity. As this material falls inward, it accelerates and heats up, emitting radiation in the process. In more active black holes, This forms a bright, dense accretion disk, a luminous structure that can outshine entire galaxies. Sagittarius A does not display such a dramatic disk. Instead, its accretion flow is sparse, irregular, and relatively faint. The surrounding region does not supply it with a constant stream of material, so it exists in a state of low activity. The gas that does approach it tends to be thinly distributed, forming a diffuse, turbulent environment rather than a stable, glowing disk. Even so, the motion of this material is extreme. Close to the black hole, matter orbits at a significant fraction of the speed of light, completing rotations in minutes or hours rather than years. Magnetic fields twist and reconnect, releasing bursts of energy. Occasionally, small clumps of gas fall inward more rapidly, producing short-lived flares that can be detected in infrared and X-ray wavelengths. These flares are not dramatic on a cosmic scale, but they are reminders that the system is dynamic. There is a tendency to think of black holes as consuming everything around them, as if they were cosmic vacuums pulling in matter indiscriminately. But this is not how they behave. At large distances, their gravitational influence is no different from any other object of the same mass. If the Sun were replaced by a black hole of equal mass, the Earth would continue to orbit in exactly the same way. The path would not change, because gravity at that distance depends only on mass, not on the nature of the object. The difference emerges only when you move close. Near Sagittarius A, the concentration of mass within such a small volume creates conditions that do not exist elsewhere. Orbits become tighter, velocities increase, and the effects of general relativity begin to dominate. Space and time are no longer behaving independently, but as parts of a single structure that can be bent, stretched, and curved. One of the consequences of this is that time itself does not pass at the same rate everywhere. The closer you move to a massive object, the slower time passes relative to a distant observer. This effect is negligible near Earth, measurable only with precise instruments, but near a black hole, it becomes significant. Clocks closer to Sagittarius A tick more slowly than those farther away. The difference grows as you approach the event horizon, becoming extreme in its immediate vicinity. This is not a matter of perception, but of physics. If an object were to orbit very close to the event horizon, time for that object would pass more slowly compared to an observer at a safe distance. From its perspective, nothing unusual would occur locally. But when compared to the outside universe, the difference would become apparent. Processes that take hours or days for the object might correspond to much longer periods for someone observing from afar. And as you move closer still, toward the boundary itself, the effects intensify. From the perspective of a distant observer, an object approaching the event horizon would appear to slow down, its motion stretching out over time, its light shifting toward longer wavelengths, fading as it approaches the threshold. It would never be seen to cross the boundary, only to approach it asymptotically, becoming dimmer and slower until it effectively disappears. From the perspective of the object itself, the experience would be different. It would continue inward, without noticing a sudden change at the event horizon, crossing a boundary that has no physical marker. But beyond that point, all possible paths lead further inward, toward regions where our current understanding of physics can no longer provide clear descriptions. These are not effects that occur at a distance. They are confined to the immediate environment of the black hole, within a region that, while small on a galactic scale, contains some of the most extreme conditions in the universe. And yet, all of this exists quietly at the center of the Milky Way. Sagittarius A does not blaze across the sky. It does not dominate our observations with overwhelming brightness. It remains hidden, revealed only through careful measurement and indirect imaging, its presence inferred through the behavior of light and matter rather than directly seen. But the structure we have uncovered, the ring of light, the shadow at its center, the dynamic flow of material around it, is not unique to this one object. It is a manifestation of the same underlying physics that governs black holes everywhere. What makes Sagittarius a distinct is not what it is, but where it is. It is not a distant curiosity, located in another galaxy, observed across vast expanses of space. It is part of our own system, the central point around which the Milky Way is organized. Every orbit within the inner regions of the galaxy is influenced by it. Every trajectory near the core is shaped by its presence. And although its influence weakens with distance, becoming one contribution among many in the outer regions of the galaxy, it remains the reference point, the central coordinate, the place from which distances and motions are often measured. A fixed point, not in the sense of being stationary, but in the sense of being central, and everything else moves in relation to it. Distance softens everything. From where we are, Sagittarius A is an idea more than a place, something defined by numbers, images, and motion, traced across years of observation. But if you begin to close that distance, even in thought, the nature of it starts to change. Not suddenly, not with a clear boundary, but gradually, as the environment becomes less familiar and the assumptions we rely on begin to lose their accuracy. Far from the center, the galaxy behaves in a way that feels stable. Stars follow wide, predictable paths, separated by vast distances, moving slowly enough that change is almost imperceptible across a human lifetime. Gravity is present, but it is balanced, distributed across the combined mass of everything in the galaxy. There is no single point that dominates your immediate surroundings. As you move inward, that balance begins to shift. The density of stars increases. Distances between systems shrink. The background of the sky becomes brighter, not because of a single source, but because there are simply more stars packed into a smaller volume. Motion becomes more apparent. Orbits tighten. Velocities increase. The calm, sparse structure of the outer galaxy gives way to a more crowded and dynamic environment. Closer still, the influence of Sagittarius A begins to stand out. Stars no longer move as if they are part of a broad, distributed system. Their paths curve more sharply, their speeds rise dramatically, and their trajectories begin to reflect the presence of a dominant central mass. This is the region where individual stellar orbits, like that of S2, become tightly bound to the black hole, tracing elongated paths that carry them deep into its gravitational field before sending them back outward again. If you were to follow one of these paths, the change would not feel abrupt. There would be no moment where you cross into a different kind of space. Instead, the differences would accumulate. Your velocity would increase as you fell inward, not because something is pulling you in a directional sense, but because the curvature of spacetime is guiding your motion along a path that leads closer to the center. The sky itself would begin to change. Light from distant stars would no longer travel in straight lines. As it passes near Sagittarius A, its path would bend, curving around the mass of the black hole. Objects that should be hidden behind it would appear displaced, their light redirected toward you. The background would distort, stretched, and warped into arcs and rings, not because the objects themselves have changed, but because the space between you and them is no longer flat. This effect, known as gravitational lensing, becomes more pronounced as you approach. Stars that once appeared as distinct points begin to smear into curved streaks of light. Some appear in multiple places at once, their light taking different paths around the black hole before reaching you. The closer you move, the more extreme these distortions become, until the sky is no longer a familiar arrangement of stars, but a shifting pattern shaped by gravity itself. At the same time, your motion continues to accelerate. In the outer regions of the galaxy, orbital speeds are measured in hundreds of kilometers per second. Near Sagittarius A, they rise into the thousands. Close to the black hole, matter can orbit at a significant fraction of the speed of light. If you were following a stable orbit at that distance, your path around the center would take minutes or hours rather than millions of years. Speed in this environment is not a choice. It is a consequence. The closer you move, the faster you must travel to remain in orbit. If your path brings you too close, there is no stable orbit available. All trajectories begin to lead inward, not as a matter of force, but as a matter of geometry. The structure of spacetime itself narrows the set of possible paths until they converge. And as that happens, another effect begins to emerge, one that is less visible, but more fundamental. The strength of gravity is not uniform across space. Even on Earth, there is a slight difference between the pull you feel at your feet and the pull at your head, but it is so small that it goes unnoticed. Near a black hole, this difference becomes significant. The gravitational field changes rapidly over short distances, creating what are known as tidal forces. If you were to approach Sagittarius A closely enough, these forces would begin to act on your body. The side of you closer to the black hole would experience a stronger pull than the side farther away. This difference would stretch you along the direction of the gravitational gradient, while compressing you in the perpendicular directions. The effect is gradual at first, increasing as you move closer, becoming more pronounced as the gradient steepens. For a supermassive black hole like Sagittarius A, this process does not begin far from the event horizon. Because the mass is spread over a relatively large radius, the tidal forces at the boundary itself are weaker than those near smaller black holes. This means that, in principle, it is possible to cross the event horizon without experiencing extreme tidal effects immediately. The environment would still be hostile in other ways, but the transition itself would not involve an abrupt physical disruption at the boundary. The boundary, as described earlier, is not a surface. There is no visible line marking the point of no return. From your perspective, as you approach it, nothing would indicate that you are about to cross into a region where escape is no longer possible. Your instruments would continue to function. The laws of physics, as far as they can be measured locally, would appear unchanged. But the relationship between you and the rest of the universe would begin to diverge. To a distant observer, your approach to the event horizon would appear to slow down. Light emitted from your position would take longer to reach them, stretched by the effects of gravity, shifted toward longer wavelengths, gradually fading. Your motion would seem to decelerate, not because you are actually slowing down, but because the information describing your motion is taking increasingly longer to escape. You would appear to linger near the boundary, never quite crossing it. From your own perspective, there would be no such delay. Time would pass normally. Your motion would continue inward. You would cross the event horizon in a finite amount of time, without encountering a physical barrier, without noticing a sudden change in your immediate surroundings. But beyond that point, the structure of spacetime ensures that all possible paths lead deeper inward. There is no direction you can move that leads back out. Not because you are being pulled in a conventional sense, but because the geometry of space has been altered in such a way that the concept of outward no longer applies. Every future-directed path points toward the center. And as you continue inward, the effects that were once subtle become dominant. The curvature of space-time increases. The differences in gravitational pull across your body grow stronger. The environment becomes increasingly extreme, not just in terms of force, but in terms of how space and time themselves behave. Our current theories can describe some aspects of this regime, but they begin to break down as you approach the central region. At the core of a black hole, our equations predict a singularity, a point where density becomes infinite and the known laws of physics cease to provide meaningful answers. Whether this represents a true physical reality or a limitation of our models is still an open question. What is clear is that we do not yet have a complete description of what happens in this region, so any attempt to describe it remains incomplete. What can be described, however, is the relationship between time near the black hole and time far away from it. As you move deeper into the gravitational field, time for you continues to pass at its normal rate, but compared to the outside universe, it becomes increasingly offset. If you could observe the distant galaxy from a position close to the event horizon, you would see processes unfolding more rapidly than expected. Stars would evolve, move, and change on compressed timescales. The wider universe would appear to accelerate, not because it is actually speeding up, but because your local time is progressing more slowly relative to it. This effect grows stronger the closer you move to the boundary. Near the event horizon, the difference becomes extreme. From your perspective, the external universe could appear to evolve through vast stretches of time, while you experience only a short duration. Light from distant regions would arrive increasingly blue-shifted, carrying information from a future that is, from your frame of reference, approaching rapidly. And yet, this is not something that can be sustained indefinitely. The environment near a black hole is not a place where stable observation can continue without limit. The same forces that create these effects also impose constraints on how long any structure can remain intact. The deeper you move, the more intense the gradients become, and the more extreme the conditions you encounter. What this reveals is not just the behavior of matter near a black hole, but the nature of space and time themselves. Sagittarius A is not simply an object with mass. It is a region where the geometry of the universe is altered in a fundamental way, where the familiar separation between space and time breaks down into a single, interconnected structure that can be curved, distorted. And all of this exists at the center of the galaxy, quietly, continuously, shaping the motion of everything around it. From a distance, it is an anchor, a point that defines the structure of the Milky Way. Up close, it is something else entirely, not just a source of gravity, but a place where the rules that govern the rest of the universe begin to change. And yet, despite how extreme it is, it remains part of the same system you are in now, the same galaxy, the same structure, the same orbit that carries you, slowly and steadily, around it. Sagittarius A can feel singular when you focus on it long enough, as though it occupies a unique place in the universe simply because it sits at the center of our own galaxy. But in a broader context, it is one example of a much larger class of objects, part of a spectrum that spans an enormous range of scales. Black holes do not all share the same origin or size. At one end are stellar mass black holes, formed from the collapse of individual stars. These objects typically contain a few times the mass of the Sun, sometimes more, compressed into a region only a few tens of kilometers across. They are scattered throughout galaxies, remnants of massive stars that reached the end of their life cycles and collapsed under their own gravity. At the other end are ultramassive black holes containing tens of billions of solar masses. These exist at the centers of the largest galaxies, far exceeding the scale of Sagittarius A. The black hole in M87, which was imaged before Sagittarius A, is already much larger, containing billions of solar masses. And beyond that, there are even more extreme examples. Objects so large that their influence extends across vast regions of space. Sagittarius A sits somewhere between these extremes. It is far more massive than any stellar remnant, yet small compared to the largest known black holes. Its scale is enough to dominate the inner regions of the Milky Way, but not enough to define the entire galaxy on its own. It is significant, but it is not exceptional in a universal sense. There are countless galaxies, each with their own central black hole, many of them larger, some smaller, all following similar underlying principles. This raises an important distinction. While Sagittarius A sits at the center of the Milky Way, it is not the sole reason the galaxy holds together. The structure of the Milky Way is determined by the combined mass of everything it contains: stars, gas, dust, and something more elusive that does not emit light at all. Dark matter forms an extended halo around the galaxy, a vast, invisible distribution of mass that contributes significantly to its gravitational stability. Without it, the outer regions of the galaxy would not behave as they do. The black hole's influence is strongest near the center. Within a relatively small region, its gravity dominates, shaping the motion of nearby stars and gas. But as you move outward, its contribution becomes just one part of a much larger system. The orbits of stars like our Sun are governed not by Sagittarius A alone, but by the total mass enclosed within their paths. This means that while we are connected to the black hole, we are not bound to it directly in the way a planet is bound to a star. We are part of a rotating system whose structure emerges from the sum of its components. Sagittarius A provides a reference point, a central marker, but the galaxy itself is held together by a distributed gravitational field that extends far beyond it. And yet, near the core, the environment becomes something distinct. The central region of the Milky Way is one of the most densely populated areas in the galaxy. Stars are packed closer together, moving along intersecting paths, their interactions more frequent than in the quieter outer regions. The background radiation is stronger, the presence of gas and dust more pronounced, and the overall structure more chaotic. In this environment, the influence of Sagittarius A is not subtle. Stars pass close to the black hole on elongated orbits, accelerating to extreme velocities before swinging back outward. Some may be perturbed by interactions with other stars, their paths altered in ways that bring them closer to the center. In rare cases, a star may pass too close, experiencing forces strong enough to disrupt it, tearing it apart and feeding its material into the surrounding accretion flow. These events are not common on human timescales, but they are part of the ongoing evolution of the galactic core. The region is dynamic, constantly changing, shaped by the interplay between gravity, motion, and the distribution of matter. It is not a stable, unchanging center, but a place of continuous interaction, where the presence of the black hole influences outcomes without dictating every detail. And there is evidence that this region has not always been as quiet as it appears today. Extending above and below the plane of the Milky Way are enormous structures known as the Fermi bubbles, vast lobes of high-energy radiation that stretch tens of thousands of light-years into space. Their origin is still studied, but one of the leading explanations is that they were produced by a period of increased activity at the galactic center, when Sagittarius A was consuming more material and releasing significantly more energy than it does now. If this is the case, then the black hole at the center of our galaxy has not always been subdued. At some point in the past, it may have resembled the active nuclei seen in other galaxies, emitting powerful jets or winds that shape the surrounding environment on a much larger scale. Over time, as the available material decreased, this activity would have diminished, leaving behind the quieter system we observe today. This suggests that Sagittarius A exists not in a fixed state, but as part of a long-term cycle. Its behavior depends on the material available to it, the interactions within the galactic core, and the broader evolution of the Milky Way itself. Periods of activity and inactivity may alternate over timescales far longer than human history, shaping the structure of the galaxy in ways that are only partially visible to us now. And the future holds further changes. The Milky Way is not isolated. It is moving through space, part of a larger group of galaxies, and over time, its path will bring it into interaction with others. The most significant of these is the Andromeda Galaxy, a massive spiral system that is currently on a trajectory toward the Milky Way. In several billion years, the two galaxies will begin to merge. This process will not resemble a collision in the conventional sense. Stars are separated by such large distances that direct impacts between them are unlikely. Instead, the structures of the galaxies will pass through each other, their gravitational fields interacting, reshaping their forms, redistributing stars and gas into new configurations. At the center of each galaxy lies a supermassive black hole. As the merger progresses, these two objects, Sagittarius A and the black hole at the center of Andromeda, will be drawn toward one another. Over time, they may form a binary system, orbiting a shared center of mass, gradually losing energy through interactions with surrounding matter and the emission of gravitational waves. Eventually, they may merge. When two black holes combine, the result is not just a larger black hole, but a release of energy in the form of ripples in spacetime itself. These gravitational waves propagate outward, carrying information about the masses and dynamics of the merging objects. Such events have been detected from smaller black hole mergers, but a collision between supermassive black holes would occur on a much larger scale. This is not an immediate concern. It lies far in the future, beyond the lifespan of the Sun, beyond the current configuration of the Earth. But it is part of the long-term evolution of the system we are in. Sagittarius A is not static. It is part of a sequence of events that extends across billions of years, influenced by interactions both within the Milky Way and beyond it. Its current state, quiet and relatively stable, is only one phase in that sequence. And throughout all of this, the galaxy continues to rotate. Stars follow their paths, completing orbits over immense spans of time. Some move quickly, tracing tight loops near the center. Others, like our Sun, travel more slowly, taking hundreds of millions of years to complete a single circuit. These motions are not synchronized, not coordinated, but they are all part of the same structure. A structure that persists even as its components change. Sagittarius A remains at the center, not as a controlling force over every motion, but as a defining feature of the system, a point around which the inner regions are organized, a reference that persists even as everything else evolves. And we remain within that system, moving along our own path, carried by the combined motion of everything around us, part of a galaxy that is itself in motion, part of a universe that continues to expand. The scale is difficult to hold in mind all at once. But the connection is constant. There is a tendency to think of what lies at the center of the galaxy as something distant, something separate from the moment you are in now. It sits far away, hidden behind layers of dust, revealed only through instruments and calculations, existing on scales that feel disconnected from anything immediate. But the connection is not distant. It is continuous. Every movement you make takes place within a system that is already in motion. The Earth rotates, the planet orbits the Sun, and the Sun itself moves through the galaxy, following a path that has been traced for hundreds of millions of years. None of this motion is isolated. It is layered, each scale nested within the next, forming a structure that carries everything along with it. At the largest of these scales, that motion becomes an orbit around the center of the Milky Way. The time it takes to complete one of these orbits is almost beyond comprehension. Roughly 230 million years pass between one position and the next, long enough for continents to shift, for climates to transform, for entire branches of life to appear and disappear. The last time the solar system was in its current position, the Earth was a very different place, and whatever will exist when it returns to this position again will be equally unfamiliar. This is the rhythm of the galaxy. Slow, continuous, unaffected by individual events, but shaping the broader context in which those events occur. Human history, when placed against this scale, becomes almost invisible, a brief interval within a much longer cycle. Every moment of it, every decision, every structure we have built, all of it takes place within a fraction of a single orbit. And at the center of that orbit, Sagittarius A remains. Not as something we interact with directly, not as something that exerts a noticeable force on daily life, but as a constant reference point within a system that is otherwise in motion. It does not need to be visible to define the structure. It does not need to be active to maintain its role. Its presence is enough. What makes this more difficult to grasp is that even this description, this idea of a central point, is something we never observe in real time. Everything you see is delayed. Light does not arrive instantly. It travels at a finite speed, carrying information from one place to another. Even the most immediate things are not truly present in the way they seem. The sun, as it appears in the sky, is already 8 minutes in the past. The light you see left its surface minutes ago, crossing the distance between the sun and the earth before reaching your eyes. For objects farther away, the delay becomes longer. Stars are seen as they were years or decades ago. Distant galaxies appear as they were millions or billions of years in the past. The further you look, the further back in time you are seeing, until observation becomes a kind of history, a record of events that have already occurred. Sagittarius A is part of this pattern, but at a scale that is easier to overlook. The light that reaches us from the center of the galaxy has traveled for 26,000 years. When we observe it, we are not seeing the black hole as it exists now, but as it existed when human societies were still in their earliest forms. The image constructed by the Event Horizon Telescope, the motion of stars like S2, the flares and emissions we detect, all of it belongs to a time long before the present moment. And there is no way to close that gap. No signal can travel faster than light. No observation can bypass the distance. The present state of Sagittarius A is always out of reach, not because it is hidden, but because it is separated from us by time itself. This is not unique to the galactic center. It is true for everything. What makes Sagittarius A different is that it sits at a point where distance, time, and structure all converge. It is far enough away that the delay becomes significant, central enough that it defines the motion of the system, and extreme enough that it reveals the limits of how space and time behave. It is, in a sense, a boundary. Not a boundary you can reach, but one that marks the edge of how much of the present universe can be known at any given moment. Beyond that, there is always a delay, always a separation between what is happening and what can be observed. And yet, despite that separation, the connection remains intact. You do not need to see Sagittarius A as it is now to be part of the system it defines. The orbit continues regardless of observation. The motion of the galaxy does not depend on being measured. It unfolds continuously, carrying everything within it along paths that were established long before they were understood. This includes you. Right now, without any visible indication, you are moving along that orbit. The speed has not changed. The path has not paused. It is the same motion that has carried every generation before you, the same motion that will continue long after the present moment has passed. There is no point at which you arrive at the center. no moment where the orbit resolves into stillness. The motion is constant, and the center remains distant, not just in space, but in time. It is something you move around, something that defines the structure you are part of, but not something you ever encounter directly. And perhaps that is what makes it significant. Not that it can be seen or reached, but that it exists as a fixed reference within a system where everything else is in motion. A point that remains, even as stars are born and fade, as galaxies interact and change, as the universe continues to expand. Sagittarius A is not the largest black hole. It is not the most active. It is not the most distant. But it is the one that sits at the center of the system you are in. The one that defines the orbit you are following, even if that orbit is too large to perceive, too slow to notice, too extended to ever complete within a human lifetime. And so the motion continues, uninterrupted, unobserved in real time, carried forward by the structure of the galaxy itself. You have always been part of it. From the moment you were born, you were already in motion, already following a path that extends far beyond anything immediate, part of a system that connects you to something you cannot see as it is, only as it was. And that will remain true for as long as the orbit continues.